So I saw this cool video this week on this movie, A Brilliant Young Mind, and this math channel, Mathologger, and I'll put a link down in the description, goes over an interesting scene where the character in the movie does a proof of the math problem. And I thought, you know what? That's a fun, interesting example to do as a TLA spec, just for fun. And turns out it was pretty straightforward to do. So here we go. We're going to spec, not prove, but spec the solution to the game in the movie A Brilliant Young Mind. So I have here TLA plus, and we're going to start with a blank spec, build up the spec. We're going to make a small mistake. If you watch the math video, he points out that the specification of the problem is incomplete. The game itself is missing a rule, and so we're going to pretend we're not aware of that. We're going to spec the game, and then TLC is going to show us that we've missed a case. And then we'll finish it off and clean it up. So we're going to go through 3 versions today. So it'll be a little bit of refactoring in TLA plus TLC. So here we go. First steps first, you start with your blank model, your blank TLC, your blank module. And we're going to start with the hello world of TLA plus. We have an init, we have a next, and we have a spec. The spec is defined as the init and always stuttering over, always next, allowing stuttering over the bars, and we are going to apply weak fairness over the bars for the state transition next. Okay. I have extends TLC. We're going to need sequences, and we're going to need naturals. Okay. Now, if you watch the scene in the movie, this is a game, and there are some number of cards in the game, and we're going to allow that to change. So that's going to be our variable. In the movie, he uses 20, but we want to be able to change it so that we can run the spec over various configurations of the game. So constants, num cards, and our init. We're going to also put an assumption in so that we give an indication of what we expect num cards to be. So we assume that num cards is greater than 1. We're not going to play a game with 1 card in it. That seems kind of silly. Okay. Variables, the game itself, this is the thing we're going to change over, and then just as an idiom, define the bar sequence. Could we have just put this expression right there and right there? Yeah, we could. But this is an idiom. It saves time, and as you add variables when you work on your TLA specs, you can just add them to that bars. And if you need different stuttering logic, you can split them up, but I haven't yet needed that myself. So, okay. Let's start with our init. So our init is going to be the game is equal to the function from over the input set 1 to number of cards. So we have number of cards, 1 to number of cards. So we're just building a list, 1, 2, 3, 4, whatever that value is. And we are going to map that to the string down. So all the cards are face down. We're going to say D means down. This is just an array, effectively. It's a function from the digits 1, 2, 3, 4 to the values D, 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 D. And that's exactly how you expect an array to be. So if you had Python, so in Python, you would express something like G equals 1, 2, 3, 4. Sorry, let's just do D, D, D. And you can say G0 is D, right? So the 0th element, that's the input, that's the domain of the function. It's just another way of expressing functions. So game is a function, an array, mapping digits to D. Okay. Now let's take the next set. So the next set is going to say if all the cards are face up, and remember, we're going to make there's going to be some flaws in this specification that we're going to iteratively work. So if you see something, write it down. See if you caught the mistake as we're kind of working through it together. Not really a mistake, but an incomplete definition of the model. Then unchanged, vars, else make a move. So, very straightforward. If all the cards are face up, we'll need to define what that means. Then, if all the cards are face up, the game's over, nothing happens, unchanged vars, we're done. Else, we make a move. Else, we're going to actually move a card. So let's define this first predicate, all cards face up. All cards face up is defined as for all I in the domain of game. Remember, what's the domain of game? 1, 2, 3, 4. Over game I. So that's the same as that Python behavior before. I is just an index. We're going to set it, we're going to say up. So game all I up. Is this true everywhere? That's all that's asking. Is every index of the variable game, is every index up? This is going to be true or false. Great. Now we have that one. Let's define make a move. Make move. So what we want to get to, we want to find where a card is face down, right? So we're looking for a card that's face down. So that's our predicate. So we know we're going to put it on some type of like filter condition. And we don't care which card we pick. And this is important. We don't care which card we pick, which means we could pick any of them. Therefore, it's important that we ask TLC to check all of them. So we want to use a branching condition such that TLC is aware of if you can make an arbitrary choice, then TLC is going to make every choice. In 1, 2, num cards minus 1. Num cards minus 1, which we'll see in a minute. So game, we want, when that condition is true, then the next state of game, so we want to make a change. We want to change we want to change the ith card to face up, and we want to flip the card to its right. So there's the number of cards minus 1. We wanted to go all the way to number of cards minus 1, because if we switch this card, then we're going to switch that card, because it's to its right. So we're going to say game, except I over U. So this is just saying the next state of game is going to be the current value of game in this state, except the index I, I'm going to change to a U, and except I plus 1, the value to the right, is equal to flip I plus 1 equals u, and d else u. So if the card to its right is face up, if it's face up, then make it face down, otherwise make it face up. So that's just the flip, right? Okay, we have that. We have our next, we have our spec. Let's write our type OK. Type OK is defined as all of the cards in the domain of game, such that game I in the set E for U. In all states, all indexes of game must be either face up or face down. That's all that's saying. Okay. And we have all of our pieces. Let's build a model and take a look at the picture. New model. It's just going to be model 1. Number of cards is just going to be 4. Finish. And then I'm going to go configure TLC. I'll be right back. Okay. So we're going to do additional TLC options, parameters, and I like to put this in. So when the model's small, I like to put this in, have it draw the picture, so I can look at the picture and see kind of what it's doing. So this is just going to be our game dot. Okay. And let's run this. See what it does. Okay, cool. So it did something. We need to actually configure it and tell it to do something useful. So we want it to check our type OK state. Cool. All right, so we're not breaking any rules, but are we actually completing the game? Is the game actually getting to the end state? Are we finishing? We have to define what finishing is as a temporal formula. So we want to say eventually all face up is defined as eventually always all cards face up. Okay. Control C. Go here. Go here. Add. Oops. Wrong thing. Copy. Add there. Finish. Now we're going to run this. Eventually all cards is not a state predicate, one with no primes. My mistake. I put these in the wrong box. This is a property. That is an invariant. Remove. Remove. Add. This is type OK, because that's our invariant. This is eventually. Okay. Interesting. I've never seen that error before. So you got to get your invariants and your properties in the right places, which makes sense. Okay, we're going to run this. Eventually all cards face up. Did I spell it wrong? Yep. Copy. Edit. Finish. Great. So our model completed, and we have our little state space diagram. And we can generate the picture. So dot-t PDF game dot dash o game dot PDF. And then open game dot PDF. Cool. So there's our game. Here you can start with all cards face up, and we will eventually end with all cards face down. And there are various permutations. So that's that there exists. So that's the magic of that little operator there, is because it comes to this point and it can choose any of these three, 1 to num cards minus 1, can choose any of these, it chooses all of them and it tries all permutations. And so it plays the game for us and it checks that, yes, indeed, all choices eventually end with the game face up. So that's cool. What happens, however, when we change number of cards to an odd value? So this is what's pointed out in the math video. What happens when you try and choose this very last value? In that case, we end up getting to a deadlock situation. Let's draw the picture. So here's the picture. It chooses one of these two, and one of these states eventually ends where it plays. There's no choice, but we do not end with all cards face down. Or sorry, face up. So we have a problem with our model. We need to define that extra rule that's pointed out in the video of how do we deal with choosing that last value. Okay, so let's take a step here. Basically what we need to do is we need to allow the choice of any of the cards. You can arbitrarily pick any card. And let's refactor this a little bit. So let's put this in its own little operator. Let's call this flip card to card I. Now it might feel a little dirty if you're coming from a programming background, that you just have this global variable game that you kind of manipulate everywhere. In the idioms in specifications is more about simplicity and defining that small state change. And the state of the system is inherently global. So you want to think differently about variables, global variables coming from the programming background versus the variable in TLA that's describing the state. The state really is a global concept. So it makes sense that it is accessible in that manner. Okay, so this is going to be flip card, and this is going to help us refactor this a little bit. So the problem is we can choose any one of these cards, but if we choose that card, there is nothing to its right. So what we do is the next value of game, so game in the next state, is equal to the condition if I is equal to number of cards. So if I is that greatest value, if I is all the way at the end, then game is equal to just this piece. We're just going to flip that last card. That's it. Else, game except I is equal to you and I plus 1 flip card. White space isn't sensitive there. I just wanted to line them up neatly. And that's it. Let's see what that does. Do we get our model of 3? And we do. So we complete. We have our specification. Let's run our... So here we have our 3 case, but notice it can now make 3 choices. Before it only had 2, recall? And we end in a state where all are face up. Okay, so that was cool. We can now play our game. I'm going to turn this off because it's going to get really slow. And we'll change our model to 20 and make it play the value that's actually in the game. And it runs through fairly quickly. I might speed this part of the video up. But recall in the movie they're talking about proof, so they're showing that infinite case. And we are just exhaustively checking all cases defined in this model of size 20. And there it is. It finished. So I found all games, all permutations, 10 million states with a diameter of 20. So starting from the initial state, you can get to the end state in 21 steps. That's what that diameter means. And there are 10 million permutations through that graph, and they all end in all cards face up. Cool. That was fun. Now let's take one more step, and let's put this back because this is going to be useful. And let's turn our model back down to 5. Okay. Now let's change our spec one more time, and let's make it, instead of playing just the game with 5 cards or just the game with 20 cards, let's make it play all games from up to 5 cards. So if you give it, say, hey, here's a 5-card game, let's make TLC play every game with 1, every game with 2, every game with 3. So have it sweep through those different configurations and try them all. If we would have done this first, it would have pointed out that 3 case right away. We wouldn't have had to think of it. So we're going to change this a little bit. We're going to say in the domain of game. Remember, what's the domain of game? The domain of game is 1, 2, 3, 4. We want to change what number of cards means. Number of cards is now going to define a set of games of various sizes. So we don't want to depend on number of cards in our make move anymore. So what were we using number of cards here? We were using it to represent the maximum value of that sequence. So we're just going to define the operator max with domain game. Okay, well, what does max mean? Let's write that one up real quick. Max if the set x's is equal to choosing nx in the set of x's such that for all y in the set of x's, y is less than or equal to x. If you're coming from a programming background, that feels a little awkward. It feels, hey, isn't that going to have like really horrible time complexity and really horrible space complexity? We should be more efficient. TLC does its own efficiency things. What's important in a specification is that you mathematically state something clearly. That's the essential part. So you're basically saying choose an x such that for all values, y is less than or equal to x. So x will be greater than everything. Okay, so now we have a max. We're going to choose the max over the domain. And we are going to take our init state here. We're going to change our init state, and we're going to use that branch, that fan out behavior again. So we're going to say there exists a size in the set of 1 to number of cards such that the game is equal to from 1 to the size. So now we're telling TLC, when you get to the initial state, branch on the number of cards and try all permutations of this game. Okay. We're going to change the next state a little bit, clean this up. We're going to say, and all cards are face up. So this is called an enable condition. Sorry, or all cards face up, then the game is finished, or make a move. Okay. What does game is finished mean? game finished is equal to. And the reason we're adding this other layer of variables in is it's going to change this to actually point out when it's making moves. So it's going to make the graph a little bit easier to read. That's why we're putting these extra labels in. Okay, so this is all cards face up, unchanged game. Okay. And we got to put this guy above that guy because he needs, oops, wrong thing. Okay. Init vars, type OK, size of game, domain, and max. So let's try this. Save it. Is it going to draw that? Okay, cool. Make it happen. Great. Now here's our picture, and it worked. So let's zoom in on this a little bit. And we can see that first it plays the game, well, not necessarily first, but it plays the game with a single card in it. It makes a move, and we end with all cards in face up. It then plays the game with 2 cards in it. It makes those choices, and it ends in all cards face up right there. It then plays the game with 3 cards, and then 4 cards, and so on and so on. So in this way, we've taken a spec, we've played our little game that was in the movie. TLC showed us that when we had an odd number of variables, the test actually fails. And then we take one more permutation and have it play all games up to that configuration. So that was our fun little experiment or game specification today. Thanks for joining me. See you next time.